All right, welcome to day 7 by 30 of 30 days of machine learning. So this is basically a repo dedicated to machine learning where each day we make and discuss a new model. So I made this repo as part of a revision kind of a challenge, but then it soon become became very good. Like the repos are all very detailed, the problem statements are fresh, starting from fundamentals all the way up to complicated problem statements. You can follow along the series and check out the first 6 days as well. I have put the link of the GitHub and the source code in the description. You can check it out. Without wasting time, let's move forward. What do we have on our hands today? Let's go. Today we have on our hands nothing but SMS spam classification problem using a naive Bayes classifier. All right. So first things first, we'll be following the similar pipeline that we do. So what do we do? So SMS spam classification, it's a very typical problem in NLP. NLP is natural language processing. So, if you're learning machine learning, you first start from Python, then mathematics, then the basics of machine learning, the classical models. Then you go to deep learning and then NLP. So, NLP is another topic. It's basically based on natural language, which means human language. Okay. So, it is a very classical NLP problem. And basically, we have on our hands a spam data set and we are given the task that if we get some fresh values, then based on the historical data, will our model or will we be able to accurately determine whether the messages are spam or ham? Ham is the opposite of spam. You can say not spam as well, or you can just think of it as legitimate messages. Okay. So, in this problem, we have implemented a naive Bayes classifier, and I'll be explaining as to why we chose this as the model in detail. And we also did a comparison of the naive Bayes model with logistic regression as well. Okay, so without wasting time, let's just move forward. First of all, to the data set. So I have attached the link of the data set in the description. You can check it out. It is just the spam.csv data set and it's a massive data set, more than 5,500 spam messages. It's a collection of SMS messages which are spam and ham. Okay. And of course, essentially, if we think about this carefully, this problem boils down to a binary classification problem. So this is the third binary classification problem statement out of the 30 days. And yes, all three of them are different. This is going to be different as well because this is going to be the first time that we deal with textual data. So we deal with text data pre-processing, missing value handling, all of that stuff. So I'll be getting on to that. And now getting on to that. So of course, since it's a binary classification problem, which means like a 0-1 problem, like a coin toss. It's like head or tails. So this is the encoding that we have used. Zero for spam, one for ham. This is not by convention. You can use one for spam and zero for ham as well. It literally is dependent on you. It is your choice. So there's no issues with that. Now comes the main thing. Uh, I skipped over the EDA for the last model. I just went past it very quickly because it was typical. But since now we are dealing with a different type of data, I'll be discussing the text preprocessing and the EDA pipeline in detail. So let's get into it. So the thing is, let me open the code. Yeah. So first of all, this is typical stuff again, our standard imports, visualization. These are the two goats of machine learning. Time library I have imported because in this model we calculate the real-time inference latency as well. Okay, I'll be discussing that later. This is basically everything until we go on to deep learning is going to be sklearn. So these are our models. One-hot encoder for the one-hot encoding. Standard scaler to scale them, which I don't think we are going to be using here. TF-IDF. Yes, I'll be explaining everything. Don't worry. These are our metrics. So this is standard code. This is the data set. So to run the data set, you basically upload it right here. Okay. So you can wait, I haven't connected the runtime. You can connect the runtime and store the data set on your computer and then upload it from here. Okay. From wherever you have stored it. So after that, we go on to this. So now, very important thing. This specific data set had a small problem with it, and that was that the encoding of this data set. So whenever we use this CSV files, they are basically like Excel sheets. So the encodings in them are sometimes different because we do not have appropriate tabular values. So the thing is, the encoding of this data set was actually Latin 1 encoding. Okay. But whenever we run this statement, df is equal to pd.read CSV, uh, the data frame, the pandas, it automatically assumes that the encoding is going to be UTF-8. Okay. Let me quickly write it down because this is a new thing that, at least a new thing that I learned. Maybe the viewer has already heard of it. So, what happens is that, you know, we, when we write pd.read CSV, the pandas assumes that it is UTF-8 encoding. But in this case, the model actually, the data set had Latin 1 encoding. So if we do and if we proceed like that, we basically get an error and the model will not run appropriately. So we first need to convert it to the UTF-8 encoding. So this is what we have done right here. Okay. And you know, now after the encoding to UTF-8, we move forward and we basically do the pre-processing. So we have got the label and the text in the data set. This is it. We have got only two columns in the data set. One is the label, one is the text. So the label consists of 0 or 1. The label is means the target variable, which means spam or ham. And the text contains various long lines of text separated by commas. Okay. This is how you map the values. This is all basic Python syntax. You can look it up. Okay. Now, very important, we go on to the EDA. So, in the EDA, you need to be very careful about this. The thing is that in such classification problems, the data set is often imbalanced, meaning that there might be more spam values than ham values. Okay. This is similar to what occurred in our day one churn prediction problem as well. Okay. So, this is exactly what has happened there. So, to check it out, to see as to whether, there is an actual imbalance. We do nothing but we plot a count plot using Seaborn library, and we print it right here. You can look at it. So see, it's a massive imbalance. So one was our ham, and zero was our spam. So when we look at it, we can see the spam variable. Basically, the spam label has way more data points than the ham. So this is a massive class distribution imbalance that we have on our hands. And this is very important to note, by the way, because this will contribute to what model we are going to use. Okay. So now we move forward and, we look at this. So, uh, the thing here is that we also need to calculate the message length distribution. Basically, the messages present in the data set are of different length, and we are trying to analyze if distance can be a true measurer in deciding as to which message is spam and which message is ham. So this is again like a trend-wise thing. So usually, what has happened is that spam messages are longer, like whenever you get a spam message, it is some big long message. Whereas a ham message is usually short and thoughtful. Okay. So that has happened, which is why, this message right here, this, you can see the spam message, it is just so long. Its count is going up to 600, whereas the ham stops something near about 150 or something. So this is what is happening in this case. So this is the difference that you can use. So the class distribution and the message length are very important to decide as to, which messages are longer and to basically get a differentiating factor between them. So we have got that. Uh, After that, we try to plot it because this is the KD, the kernel density estimate. It is basically a histogram. We give it different colors and we plot it up. Okay. This is the message length. We show it. Okay. Now, this is very important. This is now we are heading into the text pre-processing pipeline. So whenever we are dealing with textual data, there are a few things that we need to take care of. First of all, is that wherever we have empty spaces or white spaces, we need to get rid of them. Okay. Because empty spaces do not count as characters in the data set. But if we don't remove them, the data will use them to train the model, which we don't want. So we remove the empty spaces, and at the same time we convert all the words in the data set to lowercase characters. It is the basic part of any text pre-processing pipeline. Okay, so that is what we are doing here to clean the data. Okay, this is what's happening. We convert all the spam and ham messages to a list. So then we print this. You can see this as well. If I printed it, I see this will print us the spam length and this will print us the ham length. Okay, simple. Now we move on forward. So, we are now, I think this is it for the pre-processing pipeline. Now, very important thing, we use a new thing here, which is called as WordCloud. You can see this here, it was imported. Now, what WordCloud does is that it counts the word frequencies. So let's say that I had a spam message and it sounded like free poker tokens available, something like this. So the word free is going to be repeated a lot of times. If you have a spam deal from Zomato or Swiggy, the word free is just so popular that it is used in almost all the spam messages because it catches the attention of the person who's maybe using their phone, their laptop, whatever, and suddenly a notification pops up and you see free and you immediately click on it because you think that it will save you some money or that something is coming at you, something is coming for you, which is just free of cost. So the word free is uh, going to have a very high frequency in the spam. Similarly, there are words in the ham as well, which are going to have, very, very high frequency. So word cloud just plots them. How does it plot them? Let's go and check it out. So this is how it has plotted the spam word cloud. So if you look at it carefully, you can see that the words which are most frequent are bigger in size. Okay, I repeat, the words which are more frequent are bigger in size. You see how this word free is so big, it means that it has been used a lot of times. Okay, you see this word right here, class code in the, no, not class code, claim code in the top left corner. It is very small because it is not as frequent in the data set. So this is what word cloud does. It is amazing for visualizations. Similarly, there is the ham word cloud. So in the ham, we have got the word you. So this small u is used by users a lot. Ham means true messages. Let's say my friend sends me a message. So no one writes Y-O-U-U. You can just write this U letter here, which is why it is so common. Hence, it is so big in size. Then OK, day, GT, all these words which are commonly used are going to be big in size. So this is an amazing tool for text data visualization that we can use. Okay, this is word cloud. Moving forward, I think this is it for the text pre-processing pipeline. Now we slowly move on towards what we are doing with the model. So now let me go on back to the repo to move forward. This is the message length distribution. So same thing, spam and ham. Okay. Word cloud visualization. This is the same. You can check it out. This is the text pre-processing pipeline. Now, very important. After we have done the label encoding, this is the encoding that we chose, spam as 0 and ham as 1. You can take it the other way as well, spam as 1 and ham as 0. So now there's a very important concept that we use, which is the concept of TF-IDF. Okay. So it is basically a very primitive vectorization technique. This is not used in real world NLP pipelines because it is way too primitive. But like in small data sets where its execution can be clean, TF-IDF is still pretty strong, which is why I have included it here. So let me explain it entirely. So TF-IDF is nothing but a vectorization technique. So vectorization basically means that since a model cannot really read words, we convert the words to appropriate vectors. And by vectors, you can just say like a array of numbers. And then we feed that array of numbers to the model in order to train it. Now, how do we create that vector? Let's discuss that. Let me go on to the blackboard quickly. Okay, so we move in here. Yeah. So TF-IDF. Quickly write it. TF-IDF. TF-IDF, the full form is term frequency inverse document frequency. Okay. Uh, so it is basically a mathematical model. You can look at it. So the formula goes something like this. Okay. So TF-IDF, TF of, let's say, T, okay, and then D. I'll be explaining what these terms mean. Just let me write the formula first. Multiplied by log of uh, N divided by IDF DF of P. Okay. So now what is it truly doing? So the TF-IDF formula has two parts. We have the TF part and the IDF part, and both hold their own significance. So the TF part calculates the term frequency. So the term frequency is basically just like the standard probability formula, meaning that T here is nothing but the token, which means any individual word. So T is the token. Any individual word in a document, which means in a sentence, is called as a token. And any sentence is called as a document. Okay, this is just technical terms used in NLP. So D here is nothing but the document that we are, operating in the specific document. So what is happening in here is that let's say I have a sentence that let's go or let me write it otherwise, So if I write I have to go and I want to calculate the TF value for I. So how will I calculate it? I will take I. How many times is I appearing in this sentence? One. And what are the total tokens in the sentences? So I have four tokens in the sentences. One, two, three, and four. So the IDF, so the TF value is nothing but 1 upon 4, which is 0.25. Okay, simple. So the TF value is just like the probability. Now comes the IDF value, this value right here. Now, what this value is doing is that it basically takes into account as to how many documents do we have the word appearing in. So for that we take the logarithmic. N here is nothing but if I write N, this is very important by the way. This basically sets the tone for the entire model. N basically is the total number of documents, which means the total number of sentences that we are dealing with. Can be many, many. And document frequency of T. This basically means that, uh, how many documents have the word T. Okay. So, let's take this specific sentence to explain the example. Now, this is one sentence. I have to go. Okay. Now, imagine in a large data set like we have here, we have got 5,000 plus spam messages. We are going to have tons of sentences. So, except I have to go, I have, we are going to have many more sentences in the data set itself. I'm going to have something like, uh, free deal available, discount code 25%. Then some ham message will look like, I have to go to the party or I have to get ready or I am going, something like this. So the word I will be repeated many times. So this is one sentence where the word I is occurring. Let's say there was another sentence, I am eating. Okay, it's a message that you send to your friend or your friend sent to you. So now the word I is occurring again. And we saw that the word I is occurring here itself. So this is what the IDF value accounts for. The IDF value tries to calculate as to, what is the rarity of each word. Okay. How many times does a single word occur in different documents? So I here is occurring in this document I am eating, and it is occurring in the other document I have to go as well. So how do we calculate its IDF value? Very simple. We just plug in the values of the formula. So in our case right now, we have got n is equals to 2 because n is the total documents, which means the total sentences. Right now, we only have two sentences. So we take 2 and we divide it by the document frequency of the token, which means that, the number of documents where I is occurring. So I is occurring in two of them. So we do a log. of 2 by 2 is going to be nothing but log base 10 of 1. So the answer here is 0. Okay. So this is how we calculate the IDF value. So the IDF value in this case is coming out to be 0. Okay. Now look at this very carefully. Now, what was the original formula? The original formula was that we had to multiply the TF and the IDF. So our TF value is 0.25. Okay. So our TF value is 0.25 and our IDF value is 0. So what happens when we multiply this? Of course, we are getting a 0. This is very important. What does this value mean? What if it was a high value? Okay. This is what the TF-IDF model does. See, the words which repeat very often, which means the word which are frequent, TF-IDF gives them a very low score. Okay. A very insignificant sort of a score. And the words which are, rare, TF-IDF tries to bring them up and hence gives them a higher score. You can read it alongside as well. So, a word like free, which occurs, frequently in spam, but not in ham. So it gets a very high TF-IDF weight because it is very rare to appear in the ham. But in the spam, it's appearing too many times. So it might just become close to zero, like it became in the calculation that we did. Okay. So this is the intuition of TF-IDF. It is basically based on, frequencies. It assigns importance based on how frequently the word is occurring and how rare it is across all the documents. Okay. So this basically is a very intuitive model because let's say we have got I, am, the. These words are common words. They are called as stop words. They repeat too much and they are not contributing in any sense in the training of the model. We don't need them to train the model. So these words automatically get a very low score because they are frequently appearing and they're not adding much value to the model. So this suppresses the noise and amplifies the discriminative signal. Okay, so this is what the TF-IDF is doing. Now, very important, we go on to the intuition as to the main model that we run after the text pre-processing has been done. So this is how you apply the TF-IDF. You know, TF-IDF vectorizer. This is the syntax. Max features 3000 means that it is going to take 3000 of the documents in the data set at once to operate on. Then we fit on it, and this is the label. Print test split, typical. Now, before going on to the rest of the code, which is pretty easy to understand, I'll quickly explain the model physics as to what's happening. So the model is called as a naive Bayes model. Now, you can probably think about it already. Bayes is a mathematician who made the Bayes theorem, and yes, the intuition is correct. This model is based on the Bayes theorem itself, which means it is based on calculating probabilities. I'll be explaining how we work on this model in just a second. But a very important thing to discuss here is that the name of the model is naive Bayes. Okay, we write it down. The name is naive Bayes. Okay. So Bayes is clear that it is the name of a scientist. What about this naive? Okay, why is it being called naive Bayes? What's the naive thing in the naive Bayes classifier? This is actually a question that was asked to me. So naive assumption in the naive Bayes classifier is that the words are independent of each other. Okay. So, what happens is that when we are calculating the probabilities, let's say that I have a word, I am going to the gym. So in this case, what we are saying is that the probability of one word is independent of the other. This is what the naive Bayes classifier assumes. So the probability of the occurrence of the word I is independent of this word or this word or this word. This is the naive assumption in the naive Bayes classifier. Okay. It's a very popular question because it is an obvious one. Why do we even assume it? You can read it here in a more formal manner. I've included it in the repo that the words are basically conditionally independent. Again, it's kind of a stupid assumption, which is why we call it a naive assumption because this never happens in real life. In real life, this isn't true because words are actually dependent on the other words, but it does work, so we assume it. Okay. So, now let's discuss the Bayes theorem very quickly. You can read it here if you want to. So, this is the theorem on which the model is based on. So, we have got the conditional probability formula, which looks like this. So, this basically means that probability of X given that the event Y has already happened. The formula for this is nothing but the probability of X divided by the common elements in X and Y. Okay. So, X intersection Y. At the same time, we can get the probability of Y given that X has already happened as probability of Y divided by Y intersection of X. So now, as we see, the denominator in these two equations is common. So we try and exploit that basically. So, if we calculate and, we try to calculate for this value, so we can deduce the very basic result that P x given that Y has already happened multiplied by probability of. So you can see, when we calculate for this, we are going to divide and we will get something like probability of x divided by the probability of x given that y has already happened, like this. Similarly, we solve for this and get the same value. So when we write it down in like a more formal manner, we get something like this. Okay, this is the result of Bayes theorem. It is used to basically calculate the reverse probabilities. So if you are given any three of these values, you can calculate the fourth. So that's what we are doing. Let me show it to you. So this is the problem statement. Okay. Now, like Y here is the class label, which we are trying to predict this whether the mail message is spam or ham. X is the feature vector, the TF-IDF weights that we calculated just now. Then these are the words, you can see them. This Y, given that X has already happened, is called as the posterior probability. Okay, X here is called as the evidence, Y is the prior probability. X, given that Y has already happened, is called as the conditional probability or the likelihood. Okay. So this is very important as this is what we are trying to calculate based on whether our message is ham or spam. So, if I try to take an example to show to you how it works like, so, yeah. So, now coming on to the model is based on the Bayes theorem, but how does it actually work like? So this is the official statement. So the thing is, the naive Bayes classifier has different types that we can use. We have the Bernoulli naive Bayes, we have the multinomial, we have the Gaussian as well. So all three of them have their specific strengths and their basically their advantages and disadvantages, which vary depending on what kind of data set we are working with. So if we are dealing with the TF-IDF values, some kind of a data where count, probability, and frequencies are involved. In that case, our problem is tailor-made for the multinomial naive Bayes problem. Okay. Bernoulli naive Bayes also seems like a very close second option because in here, we can basically get the Bernoulli naive Bayes is basically same as the multinomial except that it works only for binary data. Okay, so this is also very good fit for the model that we have built. So, if we take the multinomial naive Bayes and I try to explain it, this is its likelihood model, basically the formula that it works on. Here, WI is nothing but the word in the vocabulary, the ith word in the vocabulary. Okay, and this is the summation of products over all the vocabularies. Now, the thing is that probability scores usually take a very low value. You see, we are calculating the probability of word with respect to the label, and then we are doing a power of xi. This value is going to explode a lot, and then we are doing a product. So, probability values are very small. Let me show it to you if I do it for you. Okay. So, probability values are usually very small. So, let me write it. Our original formula for the multinomial naive Bayes looks something like this. This is nothing but the summation of products, which means product over I terms, probability of ith word in the document with respect to y, which means y has already happened. What is the probability that the word wi will occur to the power of xi? Now, this probability value, as we know, probability lies between 0 and 1. So this value is going to be some small value. And when we multiply a lot of small values with each other, it leads to an even smaller value. Now these kind of complex probability values become non-interpretable. They are not clear. There's tons of ambiguity. So to make them interpretable, we do a very neat mathematical trick. We take the log. Okay. We take the log like we have taken here. So we calculate the log score and then we use it to analyze. The final score, we do something like this, take a log and we then do the summation. So when you do the when you put the log operator over the multiplication summation, it becomes the addition summation. So you take, wait a second, you take I, can be from 1 or 0, whatever, we just write I here. The x of I, which was in the exponent right here, see, we had x of I in the exponent right here. We take it and rather put it here, log rules, and then we multiply with log p and probability of the word with respect to y. This is what the final score looks like. Okay, so this is the stuff. Now, this is a more interpretable value because log values are larger in magnitude, larger in scale, and hence they can be interpreted very well. So you can read it. Now, if we try to understand as to what this is doing, okay, yeah, sure. We calculated some mathematical model which looks like this, and we are saying that, yeah, we are, calculating whether this message is going to be spam or ham, and this formula is running behind. But how is it running behind? What is it actually doing? So this I have included an example. You can read it. So this is how the model is working in practice. Let's say we send a message. This is the message. Congratulations, you have won a free prize call now. So the model now calculates everything in it. It basically will calculate values for both the labels. So if we want to check whether this value belongs to spam or ham, we basically calculate this value for both of them. So if we try to calculate score and we write ham here, so we calculate the above formula for ham. So, we basically run this formula. So log probability of ham add. Now, very important, what is this x of I here? This x of I. So if you go and check it out, what's the x of I? X of I is the count of word I in the message. So in this way, we can see, let's say, the count of the word congratulations. Now, how many times is the word congratulations occurring in this message? It is occurring once. So x of I is nothing but 1. Okay. So we write 1 here. Then we have got log probability of the word with respect to y. So we write log probability of the word. What is the word? The word is nothing but congratulations. So I'm writing Kong to short it down. And Y is nothing but the label which we have chosen to be ham. This is what we are going to be calculating. Okay. Yeah. This is what we are going to be calculating. Similarly, we are going to be calculating the score for spam as well. The score of spam, and then we are going to write everything down for ham except that replace spam here and replace spam here. Now when we get these two scores, whichever score has the higher value is the one where we assign the label. So if the spam score has the higher value, it means that this message is a spam message, this message that we chose right here. Otherwise we can say that this message is a ham message. This is how the model works like. Okay. This formula is just a very simple formula that we have modified from the Bayes theorem itself. So it is basically calculating the likelihood or the conditional probability for all the words. Okay. And then we are taking the log for ease of calculation. This is a very neat mathematical trick. See, to avoid numerical underflow. Overflow means that that the numbers become too large. Here, like I said, since we are dealing with very small probability values, they are going to become very, very small values, which are not interpretable. So we take the log and we calculate it. Okay, the spam scores, obviously, they accumulate the higher values. The ham accumulates low values for the same tokens. And so the model assigns that this sentence is a spam message. This is how it works like. Okay. Now, this is the multinomial naive Bayes model. Now, the Bernoulli model and the Gaussian model are a bit different, and I'll get to them later. But first of all, we need to just include this very important math concept of Laplace smoothing. So, Laplace smoothing, you might have used this concept in pure mathematics and probability. So, this is where it is applied on. So, you can see it. So, let's take an example. Let's say that while doing the calculations, I get a calculation like this, and I get the probability of the word, any word, and I get this conditional probability to be zero. So I'm calculating some, score, some likelihood score, and I get the probability of the word, given that it is spam, to be zero. Now, what's going to happen is you saw in this formula how we are calculating the product of all the likelihoods, the product of all the evidences right here. See, this is the product operator. So the thing is, if any one of these values becomes zero, this entire score will amount to zero and it will be irrelevant to contribute to the model. Let's say that in this score, we are getting this W of I with respect to Y. And by mistake, one of them is like this and it points to zero. This way, the entire score will be pointing to zero and it will get cancelled. Okay. So this is a huge problem because what we are doing is we are ignoring the other evidences which were actually pointing to some good features in the model, which are pointing to getting some good likelihood. So we need to fix that accordingly. For that, we introduce a concept of Laplace smoothing. So for that, what we do is we add a small constant value to the probability so that it never becomes zero. So, in this we use alpha, which is called as a Laplace smoothing parameter. So we add this parameter while calculating the probability. This way, this probability score, even if it is actually zero, it never becomes zero. It just becomes like a very small, insignificant value. So that our eventual probability does not amount to zero. This is a very good trick that you can try. Okay, this is the symbols explained in the repo. So if someone is reading it without watching the video, they can actually understand everything. Okay, this is very important, by the way, and as this prevents the model from being driven to zero. It is used in other ML models as well. Then this is the model comparison. So like I said, Bernoulli naive Bayes is also a close fit to this problem statement, but there are a few differences. You see, Bernoulli naive Bayes is a very strict kind of a classifier. It is a strict 0-1 classifier, which means that either the message is going to be spam or the message is going to be ham. It doesn't really go for values in the middle. Now, what happens in this case is that it penalizes the absence of words. So let's say that there's a word free, which appears a lot in spam. But there is a message that does not contain free. Let's say there are four messages. Okay, so it's like free coupon, free deal, free food. And the fourth message is also spam message, but it does not contain the word free. So what's going to happen is that the model is going to automatically push that words toward ham. Why is that? Because it is saying that mostly spam message consists of the word free. If it does not contain free, then it must be ham. Now that might not be true. Okay. Because the model's assumption here is that spam messages mostly have free. This one does not. So put it in ham. So this is the issue here. Multinomial naive Bayes ignores the absent words, but Bernoulli naive Bayes tries to use them as evidence. Okay. So this is the log score form of its formula. This is its likelihood model. It is obviously different from the multinomial one. Now look at this formula very carefully. This xi is the binary indicator, which means either the word is present or absent. So if xi becomes zero, one of these terms gets cancelled. See, if xi here becomes zero, this entire term becomes one. And if xi becomes 1, then this entire term becomes 1. So this is very clean and intuitive to do. So if any one value is achieved, either 1 or 0, so in that way the word either becomes absent or it becomes present. There is no middle ground there. That is the only disadvantage of Bernoulli naive Bayes. Okay. There's the Gaussian naive Bayes. I've included it, but it has nothing to do with the model that we have built. As the name suggests, it is Gaussian, so it tries to assume that our data set has a Gaussian type of a distribution, which means a bell curve distribution. But this is more suitable for real world kind of data, such as sensor data, height or weight data, something like that. This here is spam classification, so it will not model very well to this, but I've included it. You can read about it. This is the reason why we, avoided this. Very important. Also, one very important feature which I forgot to mention. So, when we calculate the TF-IDF weights, okay, the TF-IDF vectors for our model, since the spam messages are a lot in number than the ham messages, the TF-IDF values are sparse, which means that most of those values are zero. Okay, they're very long matrices, but most of them are zero. Only a few values consist of good data. So they are not very close to Gaussian distributions. They are very sparse. They're very, they're not dense. They're non-negative. And they are based on the counting or the frequency that we have done. This type of data is always tailor-made for the multinomial naive Bayes classifier problem, which is why this is what we try and push for here. Okay. Now, this is pretty important. Why didn't we use a logistic regression like we did in the churn classification problem on day one? So we have actually tried for a logistic regression problem as well, because logistic regression does map very well here. It is also 0-1 binary classification type of a model, but they are both essentially very different. So logistic regression is like a discriminative model. It just tries to form a boundary between the two target variables, the two target classes. Multinomial naive Bayes is more on mathematical, probabilistic representations. It is more intuitive to use, and everything is absolutely clear. This model is probably the most white box model to ever exist, because everything is formula based and it can be derived using pen and paper. Okay. So this was the reason to use multinomial naive Bayes. We have compared the metrics of naive Bayes and logistic regression as well. Let me quickly get back to the code. So, this is the rest of the code. This is how we train for the naive Bayes classifier. Okay. Fit on this. Alpha is equals to 1. Now, this alpha is the same Laplace smoothing parameter that we have added. Okay, this is very important. This is the same Laplace smoothing parameter that I added right here. Okay, wait a second. See, so over here, just a second, right here. Okay, so that the probability values do not become zero. This alpha value again, it is usually taken as one, can be less than one or greater than one as well, but we just want to be safe and we take it as one and we move forward with it. Now, this is the training time, so we has calculated the training time in this case. Starting time, these are the predictions, these are the probabilities, and this is the inference time. So very important, I've included a new trick here, a new metric that we can use in our models. So, if I go on to, wait a second, yeah. So, if we want to calculate the inference latency, is a very important metric in machine learning models. Inference latency means nothing but the per sample latency estimate. Okay. Latency is basically the time taken for the model to run during the predictions. That is the inference latency. So what is the per sample value of that? It is called as inference latency. Okay. The formula is the total time taken by the model to run. You can write it as T predict, you can write it as T total, whatever, divided by N, where N is the number of samples. This is the formula. Okay. So this is what we run here to calculate the inference frequency time. Like I said, we did a comparison with logistic regression on this same data set. So this is how we run for the logistic regression. Probability values to compare in the end. Inference latency values for the logistic regression as well. These are the metrics and the confusion matrix. I'll be discussing the ROC values as it is the most important thing to discuss in the entire module. So let me quickly open it in the repo itself. Okay. So these are the models that we compared. Okay. You can read about the physics of the model here. It is the same. So these are the values that we achieve for the multinomial, for the Bernoulli, and for the logistic regression. So the thing is, since we pushed for a multinomial naive Bayes model, still in this case, we saw that the Bernoulli model beat it by a slight margin. So it has a slightly higher accuracy and a slightly higher precision value. So Bernoulli naive Bayes does work very well here. This is the confusion matrix, so you can read it. This is the ROC value. So the ROC value basically plots the rate of the true positive rate and the false positive rate. So when you divide them, you get the ROC values. It basically gives you an idea as to how good the model is in, doing the separation of the two classes among all the thresholds. So this line, this green line is used as like a this line basically stands for a weak model, like the average model. If our models were close to this, the model would have been considered weak because this line means that the model is randomly guessing. It's like a coin toss. A strong ROC curve is always towards this corner, the top left corner. And our logistic regression and naive Bayes model both are towards that, and there's hardly any difference in that. Okay. This is another visualization that you can see. So we have plotted the top spam words and their log probability values. So these values right here are negative because they are not probability values. They are log probability values. So let's say that, we were getting some probability values anywhere between 0 and 1. So let's say we got a value of zero point 0.5. So we are getting the probability as zero point 0.5. We take its log, okay, and we plot it. Now the log of this is something negative, something like this. Okay, that is what has been plotted here, which is why you can see that these values are negative. Okay, this is the Nokia is the top spam word, then free, TXT, urgent. These are the top spam words involved. Okay. These are the engineering trade-offs. So training speed in multinomial naive Bayes is very fast because it is just probability calculations. And like I said, mathematical calculations always make the model very fast. Inference latency, which means the total time to run all the predictions divided by the number of samples. That is very low. Again, the model is super fast in doing the predictions. Memory used is very low because it only stores some of the probability values. Expressiveness is limited again because, multinomial naive Bayes models do not work for massive data sets. Okay. There's the failure case analysis. Basically, this includes some common cases where the naive Bayes model might just fail. So, some messages where the message seems like a spam message, but is actually a not spam message. So you can read this as well. An example like, hey, I saw you won something last week. Now this has, hey, then I saw you won. These are all words which look like spam, but they are not actually spam. The model might do a misclassification in this case, which is come on, that's just not good for us. Okay. Then there's this as well, the context and sender identity. So, call me when you're free is a message that maybe your friend sends to you. And it has the word free. So the model might get triggered and think since the word free is mentioned, there's a spam message, whereas it is not. So these are some issues that happen. There's the time complexity. Like I said, it's a linear model, very fast, n into d. D is the vocabulary size, and n is the number of training documents. Okay. So this is how you can calculate it. Space complexity. The model only stores the vocabulary for both the classes. So it's near about constant. And it's pretty small. You can really just avoid it. This is the real-time inference latency that we calculated per message. So both models are pretty fast, but as you can see, logistic regression is a bit faster than the naive Bayes model in this case because the data set is pretty small. If it was a larger data set, maybe they would have a value which is even closer. So these are both very practical options to explore while choosing a spam or not spam kind of a model. Okay. So this is the model physics again, which you can really read about. This is all very readable. None of this is theory which is bookish. I've tried to make it as intuitive as possible. So you can check it out. Of course, the model is based on the Bayes theorem. Okay. So this is, I think, going to be it for the uh, spam classification problem statement. Confusion matrix, again, 0, 0, typical. 1, 1 is the true positive values. Now we are getting a high value of true positives, which is very good. And these are the ratios of true positive and, the total positive, which is the precision. We have got the recall, F1 score. We have got good values overall. So it is a very good thing. Uh, this is the inference latency that we calculated. So this is going to be it for the model. The main thing in this model is to understand as to where to apply it and where to completely avoid it. And it is basically based on the conditional probability model given to us by the Bayes theorem. And, if we want like like a general working rule, we can say that if we have got a binary classification problem, we should opt for a Bernoulli naive Bayes kind of a solution. But since in this case, our data was very sparse and the distribution was different as well, we try to go for multinomial naive Bayes as well. And if the data set resembles something like a real life data set, then of course we go for a Gaussian distribution and hence a Gaussian naive Bayes model. So this is the comparison of the model. Let me check if something is remaining. Yeah, very important point. Log in the calculations is used. You can see it here. Okay. This is specifically used in order to, reduce the calculations that we are trying to make. You can see, how we put the log here. This is very good as it basically makes the values more interpretable and our calculations easier. So you can try it out as well. And yeah, this is it for day 7. I'll see you on day 8. Let's see what the problem we have on day 8. So for day 8, we have got on our hands an insurance expense prediction problem using gradient boosting. Uh, Again, a mathematically very, very sound model to use. And we'll do it tomorrow. Thank you so much.